Hello everyone. So we are starting the chapter alcohol phenols ethers today. This is from your MSc Elementary and I'll be discussing the questions from 1 to 10 in this video. So question number 1 we have been asked which of the following is a secondary alcohol. So we have these multiple compounds given, out of which I have taken the first one. And if you see the first one, this is clearly a phenolic alcohol. The phenolic alcohol is the alcohol, or you can say it is a phenol, where the OH is present on the benzene carbon. So neither it is 1 degree, nor 2 degree, nor 3 degree. It is a phenol, which is also called as phenolic alcohol. Now look at the B option. B option may the carbon on which the OH is present is attached to 2 carbons. So when that carbon is attached to 2 carbons, this carbon is 2nd degree. And the OH which is attached is also called as 2 degree. So my B option says it is a 2 degree alcohol. This is what is asked in the question also. Option number 3 may the carbon on which this OH is connected to 1 carbon here, 2nd carbon here, 3rd carbon here. So basically it is connected to 3 carbons. This is a 3 degree carbon. So on 3 degree carbon, the OH which is present is also called as 3 degree alcohol. The 4th option given is CH3OH, which is nothing else but methanol, and it doesn't have any degree. We can call it as a 0 degree alcohol also. So we have been asked 2nd degree alcohol, and 2nd degree alcohol is B. Now come to question number 2. In question number 2, it is asked what is the product of the following reaction. Now this is the reaction given. Look at the molecule very carefully. We have a CH3 over here and we have a OH on this side. SOCl2 with pyridine is capable of doing SN2 reaction. And what kind of nucleophile it is going to generate? Cl minus. So Cl minus from here is gonna do the back attack, which all of us know that SN2 is capable of doing the back attack. Okay, SN2 is the reaction where the back attack happens on the carbon carrying a delta positive charge where already existing leaving group is there. So what is the leaving group over here? OH is the leaving group. There is a delta positive charge over here. Cl minus will do a back attack, and when it will do the back attack, OH will be going out. So OH will be acting as a leaving group over here. So OH minus will be the thing. Now if you look at this, OH is away from the viewer. When Cl minus will attack on it from the back side, the orientation of the molecule will change, or you can say orientation of the incoming nucleophile will change, and the Cl minus will be the part of the carbon chain. Basically it will replace the leaving group and it will act as a nucleophile over there, and ultimately will go towards the viewer. So inversion of the configuration will take place. There is no other compound is going to form, no racemic mixture, no other thing. This is the alone thing which is going to form, and it is optically active. Why it is optically active? Because if you see, this particular carbon has 4 different groups. One is chlorine, one is hydrogen, then one chain from this side and this side. Both the sides are not symmetric. So this is an optically active single molecule forming, no racemic mixture. So according to that, the answer is D. Now come to question number 3. This is our question number 3. So in the question number 3, it has been asked what is the major product formed in the following synthesis. So we have to see what is the product forming. Now first of all, we will understand what all different reagents have been taken and what is their role. So if you see here, there is a PBr3 taken, which basically generates the Br minus species and is capable of doing SN2 reaction. Okay, after this I have another species given, which is CH3COONA, which can also be written as CH3COO minus. This is also a strong nucleophile, hence is capable of doing SN2. So what we can see in this reaction is the reaction may have 2 times SN2 happening. What is the leaving group here? OH is the leaving group. So first Br minus will back attack here, will ask the OH to go away. When it will go away, Br will get attached towards the viewer position pe. Then CH3CO minus will again do the second attack. This is how the CH3CO minus is doing the back attack again, and now it will be away from the viewer. There is an inversion here and there will be another inversion here. So 2 times inversion will happen, and hence this product will be formed, which is nothing else but the answer B. Now come to question number 4. In question number 4, it is asked which is not a likely product formed when the following alcohol is treated with sulfuric acid. First of all, we should know what is sulfuric acid. What does sulfuric acid do? So H2SO4 is the sulfuric acid, which is a dehydrating agent, and it is capable of removing water using E1 or E2 depending upon what kind of alcohol we have taken. If the alcohol is 3 degree or 2 degree, most likely the E1 is gonna happen. So E1 ka first step is the formation of a carbocation. So basically your H plus goes and protonates your alcohol, okay, and then forms OH2 plus. So this is what it forms. Now after the OH2 plus is formed, this becomes a good leaving group and it leaves the system forming carbocation. And this carbocation now has an option of rearrangement. Here though it doesn't require to rearrange because it's already at a stable position. So now after this, the base HSO4 minus will come and attack on the beta hydrogen. So this is your, or you can say now it has become an alpha position. So this is your hydrogen here, you have a hydrogen over here, and there is a one hydrogen which will be talking here. So neighboring carbon's hydrogen it will be removing. So ideally this carbon is a beta carbon with respect to the original molecule, but with respect to this carbocation, the carbon will be called as alpha carbon. So let's not get confused with alpha and beta. The next neighboring position, hydrogen will be removed by this base. So there are three options. Either my HSO4 minus can take out hydrogen from this position 1 or position 2 or position 3. So if it is taking the H from here, that is position 3, then it is going to form an alkene like this. If it is going to take the hydrogen from position 2, then it is going to form the compound this is using 3, this is using 2. And if it is removing the hydrogen from position 1, then so basically if this hydrogen is going out and going to HSO4 minus, then it is going to form this compound, which is formed by removal of the hydrogen at position 1. So these positions may say these are possible answers. So obviously not all of these are forming in the same proportion. One is major and others are minor, but these are the possible answers. So we have this option, which is the part where I have written 3 is your option B, and the one which I have written 1 is your option C, and this is your option D. So only option which is not available in the answer is your option A. So A is the answer. That means A is something which we cannot form in this reaction. Now let's talk about question number 5. So question number 5 they are asking what are the products forming after like reacting your alkene with KMnO4, cold basic KMnO4. And they have also mentioned that there are two products forming, product and its respective enantiomer. So we will understand what is the compound forming and what is the mechanism being followed here. So this is my alkene given. Here we have taken KMnO4 cold, which is a syn hydroxylation reagent. What does it mean? It means it attaches OH on double bond, that too in a syn manner. That means 2 OH, this is a double bond. This double bond may say pi bond will break and 2 OH groups will come and attach, both from the same position, both from the same orientation, you can say, from the syn position. Basically both will approach from same side. That is what is called as syn hydroxylation. So this is a weak oxidizing agent, not very strong oxidizing agent. So that means if I'm breaking this double bond and this place is quite hindered, so my OH can come from here and my another OH can come from here, and if both are facing from the same side, either these two OH will be towards the viewer, or the other possibility is both the OH can be away from the viewer. So this is how your orientation may look like, and both of these are enantiomers of each other. So this is the answer. Now come to question number 6. Now question number 6 though the molecule looks little big and maybe little scary, and they have written the reaction with CrO3 with HCl and pyridine. CrO3 with HCl and pyridine is nothing else but PCC. So all of us know how does PCC act. PCC basically oxidizes your alcohol, but what type of alcohol does it oxidizes? It oxidizes your primary alcohol to aldehyde and secondary alcohol to ketone. It doesn't oxidize the 3-degree alcohol, and it also doesn't affect the double bond. So this is the behavior of PCC. Okay, so now if you see this compound, let's figure out first what kind of alcohols do we have. This is a 2nd-degree alcohol because the carbon on which it is present is a 2nd degree, and this carbon is a 3-degree carbon, so this alcohol is 3 degree. So that means my PCC is not gonna impact this OH but only this one. So when it will impact this OH, it will oxidize my 2nd-degree alcohol to the respective ketone. So the hydrogen from here and hydrogen from here both will be removed, and ultimately C double bond O will be formed plus H2O will be produced. So this is your option D. Now let's talk about the question number 7. Question number 7 says how many compounds with the molecular formula C5H10O may be reduced with NaBH4 to form the primary alcohol. So first of all, we have to understand what can convert into primary alcohol when it gets reduced by NaBH4. So any aldehyde on reduction by NaBH4 can produce 1 degree alcohol. So that means first thing what we need to understand is the molecule must have an aldehyde group. Okay, so degree of unsaturation of this molecule is 1. That means there is one double bond only, and that double bond exists between carbon and oxygen. That we have already got to know, because there is an aldehyde what we need. Okay, so there are various structures we can form of aldehyde. This is one compound. So basically now you have to form just chain isomers of it. So this is your aldehyde, the simple straight chain, and then there's a aldehyde where one branch is there. Then here we have two branches. Over here we have an aldehyde where one branch, this is on the third position, this is on the second position. So basically chain isomers of each other. If you total number of compounds you'll count, all of these will be able to give you the 1 degree alcohol after reduction, and there are 1, 2, 3 and 4 compounds here. Now there is a question based on reduction. So which of the following compounds give 3-methyl-2-butanol upon reduction with LiLH4? Now again we'll have to understand what all can form an alcohol using LiLH4. So there is an aldehyde and ketones, they can form respective alcohols. Also esters on reduction can give you the respective alcohols. Okay, now what happens when you reduce an aldehyde? Aldehyde will give you 1 degree alcohol, ketone will give you 2 degree alcohol, and esters also give you 1 degree alcohols. Okay, so now let's see what is given. 3-methyl-2-butanol. So this is the structure of 3-methyl-2-butanol. It is basically forming a 2 degree alcohol. So when it is forming 2 degree alcohol, most likely the reaction is going to be with ketone. Let's find the ketone in the molecule. A and B both are ketones. So if I take A ka structure is something like this, and if you reduce it, the structure of the alcohol will be this, which is, I don't think is my compound. That is your 3-methyl-2-butanol. So this is 1, 2, 3, 4 and 5. This is pentanol. If you take the compound B, this is your compound B, and it is going to form, which is the expected compound. So your B is the answer. Alright, now come to question number 9. What is the question number 9 says? Again, this is the question which is based on reduction. They are asking which of the following compounds is formed in the good yield by reduction of methyl 4-oxohexanoate with LiLH4 in the ether. So they have given us the structure of 4-oxohexanoate also. This is my 4-oxohexanoate, and we are going to reduce it with LiLH4. We had discussed in the previous question also that LiLH4 reduces your aldehyde, ketone as well as ester to their respective alcohols. Now let's understand again. If I have a carbonyl group like aldehyde ketone, it gets reduced to its respective alcohol. Ketone will get converted into second degree alcohol. If I have an ester, it will get reduced on both the ways. So your chain will break into two. This OR will form ROH, and this molecule and this particular group will form the respective 1 degree alcohol. So this is how the reduction takes place. So if we'll do the same thing over here, this chain is gonna break from here, one H is gonna come here, one H is gonna come here. I can break this pi bond and one hydrogen here and one hydrogen here. So basically this carbon is also gonna form alcohol. Also this ketone will have one hydrogen here and one hydrogen here. So let me just retell you what I've just told you. So basically your ketone will form its respective alcohol, that is your 2 degree alcohol, by addition of one hydrogen here by breaking the pi bond and one hydrogen here. So this is my 2 degree alcohol will form. Now LiLH4 will cleave this bond, will form OH here, so this will be a methanol. Also it will cleave one of the bond, that is pi bond, and it will add hydrogen here and hydrogen here, and this will form this alcohol, which is a 1 degree alcohol. So this alcohol is being formed after the reaction, and the name of this alcohol is, let's start from here, 1, 2, 3, 4, 5 and 6. So hexane 1,4 diol, which is your option number B. Question number 10 again is based on the reduction process. So in this question, it is very simple question. NaBH4, what it is going to get reduced to? So it is going to get reduced to only respective alcohol, and what it is generating, it is going to generate H minus, and this H minus is going to attack on the carbon, which is the planar carbon. Okay, so CH2OH will be formed. Here there is no such specification. This carbon is not chiral, hence we cannot tell about, hence there is no enantiomer or anything being formed. So no chiral center is there, no optical activity will be there. It's a very simple straight solution, that is answer is B.